Thank you, Joe, for verifying that one for me. Um, Perfect. Okay. So, welcome. This week we are taking a break from doing some of our networking stuff and having a look at some of the best practices for Pycom devices and MicroPython. You may have noticed I posted on the forum a message earlier in the week about change of schedule. So what's happened there is we're just waiting for the PyTrack and PySense to arrive now, which should be coming in next week, and then we'll do two more Alex's Corners based around PyTrack with the GPS accelerometer, and then PySense the week after with its variety of sensors and how to use them and deploy them in the real world. So this week what we're looking at is best practices with devices and deployment. And what this means is what you should be doing with your devices if you want to put them in the real world, deploy them to a situation where they get left alone, you aren't touching them for extended periods of time, where maybe you're putting them in a remote location, whether they're mounted onto a vehicle, whether they're attached under a bridge or onto a building. Whatever they're doing, it's designing them to be able to be fault tolerant, so if something goes wrong, they can handle the errors gracefully and not just crash. Also being able to add some security measures, so for example changing the default username and password for your telnet server so someone can't come along and basically access your device. Also looking at things like ensuring that your firmware is up to date before deployment, double checking things like interrupts, making sure you're using interrupts versus loops to encourage efficiency. Looking at things like idling the CPU when you're doing tasks that require waiting. For example, if you're waiting to connect to a network, you don't want to be wasting valuable CPU cycles. So if you underclock the CPU whilst you're doing that, you can save some performance. And a number of other various tips and tricks for basically getting the most out of your device when you deploy it. We're going to be starting off looking at the boot.py file and setting up your device to be ready to go from hitting the floor and actually being deployed. So let's jump into that quickly and have a look at the boot.py script. So, okay, I'll explain to you what we're going on here. Basically, this is my classic go-to boot.py script. This is actually pulled pretty much from the documentation with a couple of tweaks. So what I normally do is when I set up, I have, you can see my library in the top left corner, I've got a config.py file. I won't open that up, but basically there's just two variables being set in there. My network SSID for the office and also the password for that network as well. It also helps me doing these videos so that I obviously don't give away my office network SSID and password over the live stream. But then you can call it simply within your function by going to config.ssid, config.password, and making sure that you've imported at the top. And then you can have all your configuration networks, protocols, whatever you want to do, place in that file, and then you just call the config script or config library per se, and grab all of the variables that you've set in there. And the value of doing this is if you need to change something on the fly, rather than have to dig through your code to work out where you've set something, you simply can just change a variable within config.py, or you can do it dynamically, do it on the run. Okay, so what we're doing here is we've got a couple of basic things. So we are importing the OS library, machine library, config, network, and then from the network the Wi-Fi. So for a lot of people this will probably be pretty straightforward. If you've been working with Pycom devices for a while, you'll know what all this does. But for people who are unfamiliar, this is basically taking all of the libraries that are required for the script and importing them. So the first line sets up our UART, so this is our serial connection. Whether you're using expansion board or another USB serial device, this basically configures the onboard UART and then sets it up for the correct baud rate, and then sets it up within the OS as well. Fairly straightforward stuff. We've touched on this in a previous live stream, so this is going to be pretty brief. Then we grab our Wi-Fi by setting up an object from the WLAN class. So this is for doing our networking over Wi-Fi. And then it gets a little bit more interesting when we go down to the next bit. So the idea of this script is basically to handle startup in two different ways. First check is looking for if the machine reset is not a soft reset. So basically, if anything's happened that wasn't intended by the user. So a soft reset is something triggered by, intentionally generally by the user. So this is something called and executed gracefully, as opposed to like a catastrophic crash or something that happened in your code that's bugged out and caused the device to reset. This basically will trigger if that has happened and it is not a machine.reset. So what this assumes is that your network connection has been set up and that your configuration, basically we're going to grab a static IP address. So the intention and reason of a static IP address is to basically be able to find a device with the same IP every time it's on your network. This is useful, for example, if you're FTPing in to use, for example, FileZilla. You know what the board's IP address is every single time. And again, this is unique to your network. So these are just settings that happen to be the case for my network. There's nothing private here. These are just IP addresses. If you were to set this up for your device, you would need to grab your own IP addresses as well. So this quickly checks to make sure that if the board had a catastrophic failure and needs to configure its IP address, runs that. And then the next if statement basically checks to see if the Wi-Fi is connected to a network or not. And if it isn't, then it runs the connection script, so grabbing the SSID from our config file and grabbing the password from the config file as well. Okay, fantastic. So that's basically the gist of the connecting script, and then we've also got the machine.idle, which is basically underclocking the CPU whilst we're waiting for the connection string to finish. And the point of this is there's a period of time where basically nothing's happening on the device whilst you're waiting to connect to the network. There's a handshake between your SciPi, Wi-Fi, LowPi, whatever you're using, and the Wi-Fi network. And what we need to do is need to wait for that handshake to be successful, return the acknowledged packets, and then say, hey, okay, we're ready to go. And then that script will finish executing, and you can boot into your main.py and do whatever you want. So I've shown you standard boot.py files before, and the only real difference here is how we handle reset calls. And the intention of this is basically to make sure that this static IP address has been handled if the device hasn't been reset via a unintentional means or by a catastrophic means. So yeah, I recommend putting some time and effort into setting up your boot.py file, because every time your device starts, this is what runs, and it can make your life a lot easier for not only development but also actual real-world deployment if you have a good boot.py script set up. So in here as well, I would also suggest that if you're setting up, for example, your Bluetooth connection, maybe LoRa, Sigfox, whatever you're doing, you can do the config in here for that as well, because obviously if your device can be deployed using them, then every time you start up, you're going to want to make sure those are initialized and set up correctly. And it also means that you can handle then all of your so-called business logic inside of your main.py and not worry about any of the config stuff. Leave that all for boot.py, which is good practice. Okay, so that's one of the first points I want to touch on. I'm going to do a list after this to sort of summarize everything and make sure that all of the key points I've touched on here are listed out and posted back to the forum. What I'll also do is just take feedback and see if there's any other points for deployment that anyone else wants to mention are useful, and maybe touch on them again next week. I know these are just kind of scratching the surface. There's lots of other things you could be doing with your devices to ensure longevity and control. So if you've got any points that I've missed or that you think are useful to have, then feel free to comment in the forum below. This will be in the link at the bottom of this video. Okay, so let's look at the next thing in the list, which is disabling unnecessary radios and anything that's not basically being used. So generally this is radios, but it could be other things like timers and things that aren't being used in your script as of current. So the main reason for this is power saving, basically. If you're running stuff and you're not actually using your Wi-Fi or you're not actually using your Bluetooth and it's connected and initiated, that's drawing precious current from your battery. And being IoT, what we're trying to do with these devices is keep them as low power and as efficient as possible. So if you're not actually using a Bluetooth or Wi-Fi connection actively, and it's going to be a substantial period of time that it's not being used for, then what you can do is deinitialize it and basically turn off or deactivate the that specific radio. So this might be a case of, for example, you have a Wi-Fi connected device using MQTT, and this is sitting doing some computation for maybe a minute or 2 minutes while it's bringing in some variables, checking some sensors, polling some various data sources. And generally there is a trade-off. You need to be able to weigh off to say, hey, look, I'm only going to be idling for say 5-6 seconds. Is there any point of me really turning off the radios for a specific protocol. And generally, if that's the case, then it probably isn't for you. But if you're going to be idling for like a minute or 2 minutes doing stuff with your data, turning sensors off and on in that period of time, then it may be worthwhile doing it. And obviously, if you're really concerned about numbers, then it's worth getting out an ammeter and actually checking how much current is being drawn whilst you're doing these processes to see if it's actually giving you any value. But for the most part, if you're idling for more than 10 seconds or so, it may be worth turning off your radios. This is worth the same case for LoRa, Wi-Fi, Bluetooth, Sigfox. Doesn't matter what it is. If it's connected and actively doing stuff, best way to save power is just deinitialize it. You can always turn it back on again. There's no problem doing that. It's just bearing in mind that if you turn it off and on multiple times, that actually does draw significant amount of current as well, as opposed to just having it on for a set period of time and it being idle itself. Yeah, so this could be used in a number of different scenarios, and this is obviously dependent on your code specifically. Okay, so one I want to quickly touch on, I don't know if there's anyone in the chat at the moment, just quickly have a check, doesn't look like it. I made the font size larger. I know this is a complaint from the week before, so just wanted to double check that that's all good. So if there's no problem with font size, don't say anything. If there is a problem, comment below and let me know if I need to change anything. I've made the PyMaker plugin terminal a bit larger as well to hopefully help. We'll probably add this feature to PyMaker later on as well to be able to actually custom do this. Right now I've just added some code to make it a little bit bigger. Okay, perfect. So what's next on the list? Telnet and your FTP server. Okay. So you may have heard about some of these recent IoT botnets or these big security issues that have been occurring in the world of IoT. And generally what the cause of these has been is that people are running connected systems, clever connected systems that have factory default settings for their username and password. And this is beyond stupid. This is a practice that should really have been abolished from anyone's code, removing the fact that you're putting devices on the internet that are connected with default passwords and default usernames. You couldn't imagine having your Mac secured to the internet without having a username and password. You couldn't imagine having your Wi-Fi connected to the internet without username and password. Same goes for an embedded device. Just because it doesn't have a screen and a keyboard doesn't mean that it's any less vulnerable to, for example, botnet attacks or any sort of malicious code that could take over your device or simply log into it with the default username and password and repurpose it. So the best way to really defend yourself against any sort of malicious attack is, if you're not using FTP for your device in an actively deployed script, is to simply disable it. So you can do this with the server.deinitialize, and this is the same thing as the previous script before. Just turn it off. If you're not using it, then there's no need to have it on. If it's not on, then it means that no one can simply connect to your board and activate the FTP server. But if you do need to have it on, make sure that you do set your username and password, and you can do this in a simple server.initialize or .init script, passing the keyword argument login, the values, username and password. So this could be, for example, Alex, and password could be Pycom underscore is the best 123. And obviously this is dependent on whatever you want to set for your username and password. Make sure you write them down before you upload the scripts and save everything to the board. Just make sure you change them from the defaults, and the defaults are MicroPython, so pretty easy to guess. Okay, so what does that bring us on to? Okay, let's look at the next point on the topic, which is resetting the device. So this is another interesting point. This is looking to do at basically critical errors and failures and how to handle resets or bugs in your code gracefully. So what I would suggest here is take a look at the machine library within documentation. Have a look at some of the things you can actually do within your code and how to handle them. So one of the good things to do is basically make sure you do all your network connecting stuff inside Bluetop UI, and then any of your complex logic that could potentially crash your device if there's any bugs or anything, or if something gets caught, handle that within your main.py. And there's two really important methods of the machine class here. These are reset and machine reset underscore cause. And right now there are two available definitions of causes. So there's the power on reset. So this is a hard physical reset of the device. And there's also the soft reset. So doing a hard power reset is effectively like the board crashing. And then a soft reset is a user-defined trigger. So for example, the machine.reset, I believe, is classified as a soft reset. And you can use this within your code, for example, to reset the state of something, to clear everything and just make sure that everything boots up correctly. You might call this after some function runs and you want to just go back to the factory state, or back to your factory state which you defined at the beginning of your code. Use this to basically power cycle effectively to remove any bugs, errors, whatever. And within machine we can have a look at a couple of other methods as well. So there is also the Sable IRQ, which, let me just double check documentation so you don't get this wrong. So this disables your interrupt requests. You might be using this, for example, to do something clever with your GPIO on the board. Maybe you want to, for a period of time, handle interrupts, and then if something's occurred in your business logic, you want to then disable that. You can use this to do that. Then is the idle, which I spoke about earlier in the Wi-Fi connecting library. This is to do with underclocking the CPU and basically conserving a little bit of power while still running the device. And then there's also the deep sleep function as well. So deep sleep will be coming soon to the devices. Daniel and the team are working very hard to make sure that's accurate and works as it should do. But for example, you can imagine that if you're doing a sensor deployed in the real world, say you're using Sigfox, you don't want to be running all the time if you're trying to conserve battery life. What you want to do, and what is basically the definition of a battery-powered IoT device, is restrict all of your functionality, all of the power-on stuff to 10, 20 seconds, and then for as long as possible, deep sleep the device. And the idea of this is that if your device is not doing anything, it should not be using any power. And in deep sleep mode, you'll be looking at drawing a few microamps of current, meaning that you can extend the life of battery for 2, 3, 4 years, depending on how big the battery is, the environment it's located in, and also how long your board is coming on for and activated whilst actually running its business logic for. So what will happen in deep sleep is once the deep sleep finishes, it'll go back and basically do effectively what's like a soft reset and start back up in the main.py. I will do another in-depth Alex's Corner on deep sleep once that's available. That's a very important feature of our devices, and it basically deserves its own Alex's Corner to fully explain everything that goes on in there. So that will be covered in more detail in the coming weeks. To be honest, what the plan will probably be is to do PyTrack, PySense, and then follow it up with deep sleep. So you can start using deep sleep with those two devices as well. But yeah, so just going back to the reset as well, sometimes you'll want to be able to handle resets. And for example, as I said, if you call reset cause at the beginning of your program and you have two different ways of handling your logic, so you handle the hard resets as well as soft resets, you can basically then account for any errors or bugs that are happening. So if you wanted to, for example, have a safe mode for your device, if something crashes, boot into safe mode, maybe wait for a confirmation message to say that, hey, look, I've sent a message up to the server to say there was a hard crash. Could someone investigate this? Or could it be flagged up for administration to basically know that a device deployed in the real world has had a hard reset for some reason? You could use that for doing a safe mode. You can also use the soft reset to say, hey, look, all the business logic executed, rather than having a while loop that executes continuously. What we'll do is we'll soft reset back to restart the main.py. And again, this is kind of really dependent on what you're doing, but it's useful to be aware of and to know about. Okay, so let's talk about, actually whilst we're talking about power resetting, we'll talk about power cycling the device. So you can also use the two to power cycle, well, hard reset to power cycle the device. And one of the values of this is that if anything's going wrong, if there's bugs in the device, or if per se there happens to be malicious code running on the device, generally we've seen botnets recently or malicious code this basically had presence within the device's RAM. If you do a power reset, you're basically flushing out all of that. So there's a really interesting article published by SparkFun, I think yesterday, the day before, talking about flushing out some of these vulnerabilities and how power cycling can be useful. I'll link that into the forum as well. It's worth having a check out about that, although that generally refers to devices running full Linux operating systems. And if you're unaware, our devices run on an ESP32, and that has basically runs on bare metal on top of RTOS, which is not the same as running a full Linux operating system. So it's worth keeping that in mind. Okay, so again, this should be drilled into everyone's heads by now, but if you haven't done a firmware update in your device for a while, what you should do is ensure that that's been done before deploying. And then obviously also run any tests or anything on your devices before you deploy again, because things do change in firmware updates. But what you should be basically doing is ensuring that whenever you deploy, you're running the very latest version of the code, because as those updates are being pushed, we are ironing out bugs, removing things that are causing potential memory issues, and adding more features to the devices as well. So it's like having a Windows machine that's running a very old service pack. For example, say you're on an old service pack of Windows XP. Obviously, you're not going to be getting all the latest updates, or you're not going to have them available to you. So make sure that you are running the latest firmware. And you can do that through our firmware update tool, which can be found at pycom.io/downloads. Okay, so one other thing I want to talk about quickly. Let me jump into Chrome to show you this one, because this is going to be coming soon as well. This will be tied into the deep sleep stuff as well. And that is actually our Watchdog Timer. So this is another thing for handling basically hang-ups, or if the code gets caught somewhere in an infinite loop. This is basically used for breaking out of that. And this currently isn't available, but will be coming soon. I've spoken to Daniel about this. The code's apparently all ready to go. We're just waiting to finish PyTrack by Sense, and then that will be pushed forward. So if you've done anything with Arduinos, it's a common practice to use Watchdog timers, and same goes for MicroPython on the Python devices. Watchdog timers are effectively a timer that runs in the background of your device that requires what's known as feeding to prevent the timer from expiring and then resetting the device. And what this would be used for is if you are running some looping in your code and you expect to see sometimes potentially hang-ups, if something gets caught, the worst thing that could happen to your device is it gets caught in an infinite loop and you can't actually break out of that loop. You can imagine that this would be particularly damaging because you've effectively got a dud device in the environment in the real world deployed. It can't do anything, it's stuck in a loop and can't break out of it somehow. So the Watchdog timer is basically looking out for that. The way that it works is you set an interval of time and you expect to have to run a wdt.feed every, in this case, 2 seconds or 2000 milliseconds. And if it doesn't receive that feed every 2000 milliseconds, then it will reset the device. So this runs basically parallel to any of the codes being executed, so that it's got its own, it's effectively thread safe, so that it's not going to interfere with anything else. It's doing its own thing. It's monitoring itself rather than running alongside your code and getting caught up in your loops as well. So a very important feature of the device, and this will be coming soon alongside the deep sleep stuff as well. So follow the forums, and as the firmware updates get released, you'll be notified of those updates. Okay, and so the last point I really want to talk about today was looking at interrupts versus loops. So this again is just more of a case of, this is, if you've done Arduino stuff, you'll be aware of this. Otherwise, it's worth keeping note of, and generally this is just to do with power performance and also usability, really. So let's jump back into Atom and take a look at that. Okay, so we've got two examples here. Let me put them side by side. Okay, so let's split this right and take a look at these. Okay, so we've got two examples here you can see on screen. Oh, we've got my camera's in the way. We can move that down. Okay, so we've got two examples here on screen. So we've got, on the left, we've got a pin being attached to an interrupt, and on the right we've got a pin being attached to a while loop. So we've got two different types of logic here. They're doing basically the same thing, but they're handling it in two different means. One is what's known as blocking, and the other one is known as unblocking, effectively. So interrupts on a device, basically the way that this works is you've got the CPU doing its activities, and there are some flags on board that can be raised and lowered depending on if interrupts are triggered per se. And we can use these for calling activities or functions to handle certain behavior if certain events occur whilst running the rest of our code. So on the right we've got the loop, which should be pretty standard if you're used to any Python coding. So this basically runs the loop, and whilst this is true, which is infinite in this case because it never breaks out the loop, it checks if the pin, which we set up earlier, is equal to 0. If it's equal to 0, it prints out something happened. That's all good and fine. However, that loop runs forever and is blocking, so you can't actually run any other code whilst this is currently running, and it locks you out. On the other hand, if you use an interrupt, what you can do is you can set up your pin, set up a callback. So basically, it sets up for two flags, and these two flags in this case are IRQ, so interrupt falling and interrupt rising. And this basically looks for a falling or rising edge on the input. So this is if you're looking at an input signal, there's a depending on whether it's coming from high to low, low to high, there will be a rising or falling edge of the pin. And if that occurs, then trigger. In this case, you probably shouldn't actually be looking for both of these. What we should be looking for really is just for one of them, because we're going to be going from a state of pull up to pull down, so we want to see the edge of the curve falling. And then once we've done that, we can handle it with what's known as a pin handler. In this case, we know then that this method triggers, and this function is then called, or this method is then called, and it prints something happened. But the way this works is because this is done in an unblocking manner, you can actually have other code as well. And later on, so you can do things like print hello Pycom. You can do other loops. You can have another loop here saying, for example, while true, print testing, and that will run. Whilst that's running, if an interrupt happens, this will basically temporarily break out the loop, run this function, and then go back to the loop again. One of the interesting things in MicroPython, or at least in our implementation of MicroPython versus other languages where you may be handling interrupts, is that you can actually put as much as you want into this interrupt method, and the device will execute it. Bear in mind, however, that this is blocking again, so whatever you call inside of your handler function, that will run until it's entirely finished. So if for example, you have like a Watchdog Timer background, you need to make sure this is fast enough to get back out of it to then feed your Watchdog Timer, or not to hang up or do any crazy stuff in the background. Yeah, so these are just some sort of tips and pointers for getting you started with your code. I mean, it's hard to give best practices because it's really dependent on what you're doing with your scenario, but be aware that these features are available, and that the likelihood is if you're doing some of the things that I've described, then they will be applicable to you, and you can use them to help make your code more efficient, more effective, and more streamlined. So these topics I will follow up in the forum thread that I've created for this week's Alex Corner. And again, if you have any other interesting or useful tips for doing deployment or looking at best practices, please do post them below. I think at some point I'll probably make a tutorial guide on the documentation that just has useful tips for doing deployment, because we also want to be able to do this for the OEM modules. These are going to be particularly interesting as well, because we're looking at those devices are going into large deployments, and if you're going to be doing MicroPython code, then you want to be 100% certain that your code is fault tolerant and can handle catastrophic errors or critical failure. So those will be particularly interesting to anyone doing OEM deployments. Okay, so unless there are any other questions, I think we'll probably call this to a close, because this week was sort of a fill-in for what I was expecting to do, which is Python PyTrack. Those are coming up hopefully next week once the documentation is all ready to go and the devices have arrived. And we'll look at those deployments as well. And you'll probably see when I start writing some of the code for them that I do actually use some of these best practices, and I'll explain again why I do things in those tutorials as well. So I will double check that we've got no questions. Perfect. Doesn't seem to be any questions this week. I did take the advice from the previous week about making font sizes larger. If there's anything else you think I should change about the video, if the audio is okay, if the lighting's funny, or if something could be changed, do let me know. I'm trying to make sure that these are suitable for anyone watching them. So you're the audience, you let me know what I can improve on. And yeah, so in that case, I will see you next week when I do the Pi track, and then 2 weeks after, once we look at PySent, and then take a look at some of the Watchdog functionality as well. So see you in a week's time.